All right, so now we're at the intermediate oxygen region, or PO2, and we want to know similarly what types of reactions are there. And for this is where we have to know a little bit more about the material. And so this is typically in a problem statement or known for a given ceramic, but we have to know something about what happens intrinsically for that material. And so for this material, we're going to say that intrinsically the stoichiometric Schottky defect dominates in these intermediate ranges where we don't have the effect of low or high oxygen partial pressure. So we have the Schottky in this region. So others might have maybe semiconductors, and so then the intrinsic electronic defect would dominate. But in this case, we're going to say that this ceramic Schottky defects are the predominant species that happens when there's really no effect of PO2. And so we're going to write that out. And again, I'm going to write it with the version on the reactant side where you can see where the metal and oxygen are located. And then we go to a vacancy on each site. And so we have this. Right? So we've written this numerous times, but here's the Schottky defect again. And we can write the other information that's going to be important. The mass action expression for S, so Schottky, is products over reactants. And we write these, but these are, as you might imagine at this point, are going to go to 1. So these go to 1. And so this is all going to be equal to the exponential of negative delta GS over KT. So we're making the assumption that Schottky defects dominate. This is in kind of our problem statement, so to speak. And so we also may consider what the minor reaction might be, right? We have this as the major one that's happening, contributing a lot of species like vacancies, but we're going to say the minor stoichiometric reaction is the intrinsic electronic reaction. So we're going to go ahead and define that, and we already know how that's written, right? We have null, so electrons and holes are in their proper valence and conduction bands, and then we form a pair, so the dash for the negative, and then a dot for the positive, so electron and electron hole. And then this is equal to Ki, which is the same as this, which we worked in the last example. So we saw that. And then this was equal to exponential of minus and then Eg for our energy, so the band gap, over Kt. All right. So again, the Schottky defects dominate. This is the main species. But then our minor species that can also happen is the intrinsic electronic. So if you're wondering, about this and what that means, this might mean that this is, instead of a semiconductor, this might be an insulator with a very large band gap, so that you don't get a lot of this until you get to really high temperatures, and so therefore vacancies dominate. So that might just be an example of what's happening here. All right, so in the next module, we're going to continue this train of thought and look at how we can start to build this diagram.